brain development, childhood to adolescence.
The human brain is the central organ of the human body and its nervous system. It is classified into many parts, each influencing a particular movement or action. The brain weighs roughly 1.4 kilos and information travels up to 120 meters per second. The brain is made up of 100 billion neurons. Neurons send information through electrical and chemical signals through the brain. Neurons are a working unit used to transmit information to another neuron to perform a particular function, for example, throwing a ball. Neurons will light up in your brain and then send a message down the spinal cord to the muscles to activate the throwing movement through your arm. The prefrontal cortex covers the front part of the brain and allows for higher levels of thinking and memory. The brain is divided into two hemispheres, left and right. It is a myth that the left hemisphere is only associated with language and more logical thinking, and the right hemisphere is only associated with emotion and creative thinking. However, even though each is more dominant in those areas, they overlap and feed from each other's side. The brain is made up of 4 segments: the frontal lobe, the parietal lobe, the occipital lobe, and the temporal lobe. The frontal lobe is located at the forefront of the brain and is responsible for behavioural functions such as theoretical thinking, organisation, and responsiveness. The parietal lobe is responsible for motor skills such as touch, sensing movement, and spatial orientation, and is situated in the front of the occipital lobe. The occipital lobe is associated with vision and sight, and it is situated at the back of the head. The temporal lobe is responsible for language and memory. It is responsible for verbal language, listening, and is situated behind the cortex. The appearance of the brain is surprisingly squishy and almost like the consistency of butter. It has a fatty covering and a wrinkled cortex that is used to protect the brain. The brain develops differently in each stage of life, including infancy, early, middle, and late childhood, and adolescence.
Brain development from infancy to early childhood.
Infancy, ages 0 to 2, is the period in which the brain is developing very rapidly and is undergoing a number of changes. In this stage, the brain is sometimes referred to as an empty sponge, ready to absorb as much information as it possibly can. Right after birth, the brain undergoes many different activities. Let's take a look at Stuart's brain development during this. Prenatally, and even after birth, Stuart's brain's neurons are going through what is called myelination. Myelination is a process by which neurons are surrounded by fat cells, which increases the speed of neural impulses as well as protect them from any other electrical interferences. Stuart, after birth, so far is unable to do any coordinated movements or perform mental operations. However, he will be able to perform physiological functions, or as I like to call it, the essentials, which are things like breathing and having a sleep-wake cycle. At birth, Stuart's brain consists of 100 billion neurons and weighs 350 grams, which is 25% of what it will weigh as an adult brain, which is 1,400 grams. By 6 months of age, Stuart's brain will weigh 50% of its adult weight, and by age 2, his brain will weigh 75% of its adult weight. This really shows how much development is going on during this age bracket, doesn't it? Another interesting fact is, as a newborn, the left hemisphere's amount of neural transmissions increases immensely when subject to speech sounds compared to the right hemisphere. This is likely because language is one of the areas that the left hemisphere typically specializes in. Stuart's brain during this stage produces twice the number of synaptic connections than are ever used. At 4 months of age, we see that Stuart's visual cortex hits its peak amount of synaptic connections, to which it then slowly reduces over time. The peak of synaptic connections produced in Stuart's prefrontal cortex generally occurs around the age of 1. This means that Stuart is developing his high-level thinking and self-regulation skills. Just because Stuart's brain is overloaded with synaptic connections does not mean that he will make use of all of them. As Stuart develops, his brain will get rid of unused or unnecessary connections. This process is called pruning. Connections which are used frequently, such as movement and motor skills, as seen when Stuart learns to crawl and walk, are generally strengthened, allowing Stuart to become better at doing those actions. Moving on, let's now take a look at Montana, who is in the early childhood age bracket. Early childhood, which is in the age bracket of 2 to 6 years, is the stage where development is still rapid and increasing. There is a big focus on areas such as motor development and language development in this stage, as children are constantly learning these things, like when you see young children learning words or running around or learning to write. Therefore, synaptic connections in areas of the brain associated with these skills will be strengthened. In this section, we'll be looking at Montana, who falls into this age bracket, and what her experiences with brain development will be. Similarly to Stuart at the age of 2, by age 3 it is expected that Montana's brain will weigh 75% of what it will weigh when it is a fully grown brain, and by the age of 5 her brain should weigh 90% of its adult weight, once again displaying the amount of development happening within these crucial years. With regard to changes in the brain, Montana's brain currently is increasing dendritic connections and is going through myelination. Myelination is important for development of skills in this stage because, as previously stated, it increases the speed of synaptic connections, improving the abilities. Myelination in areas of the brain related to hand-eye coordination are not completed until about the age of 4, which means when Montana is 4, these connections will be strengthened, therefore developing her hand-eye coordination. Researchers have found that between the ages of 3 to 6, the most rapid growth within the brain takes place in the frontal lobe, in areas associated with organisation, planning, and attention. Lastly, researchers have also discovered by taking many brain scans of children up to 4 years of age, children's brains experience rapid, distinct spurts of growth. The amount of brain material in some areas can nearly double within a year. This consequently is followed by a big loss of tissue as unneeded cells are purged and the brain continues to reorganise itself.
Brain development from middle to late childhood.
Continuing on to middle and late childhood, ages 5 to 12, we'll be looking at George's brain as it develops through this time. During this time, the prefrontal cortex shows significant development in George's brain. The prefrontal cortex is responsible for cognitive behaviour, decision-making, social behaviour and personal expression. Also during this time in George's life, his brain begins to start a process called synaptic pruning, which is where the brain starts to remove unnecessary neurons and synaptic connections and therefore allows other synaptic connections to strengthen. You may be asking yourself, how does George's brain know which connections to remove? One way to explain this is to open the debate between nature versus nurture. Nature would suggest that due to parental genetics there would be some connection in George's brain which is already stronger than others, whereas nurture would suggest that how George is raised and what environmental factors he is exposed to would be the cause of what synapses are removed. Over the course of middle and late childhood, George's cerebral cortex and cerebellum will thicken and develop further, leading to more coordination and smoother motor skills. Myelination around George's central nervous system also increases, leading to an improvement in finer motor skills. These improvements allowed George at the age of 6 to hammer, paste and tie shoes, at the age of 8 to use hands with more precision, and at the age of 10 to manipulate skills similar to adults, master intricate complex movements, and to play difficult pieces of music. This point in George's life can be known as a sensitive period for learning to speak his native language. He has until the end of late childhood, age 12, to learn to speak, with the window starting to close not long after middle childhood begins, aged 7. Also during middle and late childhood, George's brain weight will continue to increase from 95% at the start of middle childhood and fully stabilise by the end of late childhood. Now I'll pass you along to Emily, who will be talking about adolescence.
Brain development in adolescence.
What is adolescence? Adolescence is the transitional period between childhood and adulthood, typically starting at 13 through to 18 years of age. It is a time of evaluation, decision-making, commitment, and finding out identities. Let's take a look at what happens to Daisy's brain during this time. Her brain is developing rapidly, creating more network connections between brain regions. There are 4 main parts developing in her brain at this time, which include the corpus callosum, the prefrontal cortex, the limbic system, and the amygdala. First, we have the corpus callosum. This is where fibers connect the brain's hemispheres, and during adolescence, this thickens in Daisy's brain to improve her ability to process information. The prefrontal cortex is where thought process and memories are located. There is a thin outer layer of her brain that is made up of grey matter, which has the highest volume during adolescence. Her prefrontal cortex doesn't finish maturing until about 18 to 25 years of age. Her development of sensory, appetite, sexual, sensation-seeking, and risk-taking brain linkages mature first, with self-control and planning maturing later, as these are higher-level brain linkages. The limbic system is a lower subcortical system that is the main spot for emotions and experience of rewards, which matures in early adolescence. The amygdala is a part of this structure that is mainly involved in the processing of emotions. Daisy may be irrational during this time, as her prefrontal cortex is still developing and her amygdala takes over, which causes increased risk-taking behaviours and impulse decisions. During this time, Daisy may be experiencing puberty, although it can begin in childhood. It is a brain neuroendocrine process that's involved with rapid physical changes. Hormones play a role in puberty and are chemical substances that are released by the endocrine glands and carried through the body by the bloodstream. The hormone testosterone is mostly associated with boys and estrogen mostly with girls. However, testosterone levels can increase 18 times in boys and only 2 times in girls during puberty. Daisy will most likely be exposed to alcohol during adolescence. However, if she consumes an excessive amount, it will impact on her brain's development. It is not recommended for those under the age of 18 to consume any alcohol, as her brain is still undergoing rapid development. However, risky behaviour is more likely to occur when 15 to 17-year-olds drink, opposed to those older than them. So, how bad can alcohol really be? Well, alcohol consumption can lead to difficulties with learning new information and verbal skills, tiredness, which can lead to reduced concentration and memory problems, difficulties with movement and coordination, reduced capacity for problem solving, confusion and hallucinations, have a toxic effect on the central nervous system, and the wastage of brain cells due to the dehydrating effect of alcohol can all affect Daisy's intellectual development.
Perhaps now you understand the functions of brain development in a linear formation, but what happens when development isn't linear and other variables impact what we understand from these stages? Each person is an individual and recognisably develops in slightly different ways, but when looking at the impacts of trauma, those slight differences become noticeably larger. When experiencing stress, we release a hormone called cortisol. Cortisol helps people kick into gear when stress takes over, to squash our problems and rid of our worries. Cortisol is good temporarily for our survival needs. However, persistent and excessive cortisol leads to neurotoxicity in the hippocampus and prefrontal cortex, destructively impacting on brain development. People who suffer from the effects of trauma have likely experienced the longevity of cortisol, which has then led to the myelination of unhealthy synapses and the pruning of the healthy ones. Once these bad synapses have bonded and grown, it becomes extremely difficult to reverse that process. Perhaps we can link this to John Bowlby's attachment theory, advocating the fundamental importance of children having at least one primary caregiver to share a strong emotional and physical attachment to in order for optimal brain development. These bonds create the scaffolds for support and trust in humans. Without them, we see people become withdrawn from society by the lack of healthy bonds or experience of unstable relationships. Without these bonds that form support networks, people become isolated and experience excessive amounts of stress and/or trauma, which lead to destructive impacts of brain development. I was fortunate enough to have a lot more than just one primary caregiver and therefore grew up with stability and trust, providing me with the necessities to strive for my goals and maintain the stable brain development described throughout this production, which ultimately supports the importance of the attachment theory.